Hey guys, today we're looking at a very long question. This is from the May of 2022. And as I've said, we'll be looking at a wide variety of questions today. A student uses a load to pull a box up, a ramp inclined at 30 degrees, a string of constant length and negligible mass connects the box to the load that falls vertically. Okay, so the the load will be falling vertically without any intervention. The string passes over a pulley that runs on a frictionless axle. Friction acts between the base of the box and the ramp. Air resistance is negligible. Okay. So it gives us more information. The load is released and it accelerates downward, it says. Okay. Outline two differences between the momentum of the box and the momentum of the load at the same instant. Okay, so momentum is the mass times velocity. So their velocity is not going to be different. Their velocity is going to be constant. But one difference that we'll be having is that their masses are different. So the magnitude of their momentum are different. So this is our first difference. The magnitude of their momentum is different because their masses are different. The second difference that we can have is because momentum is a vector quantity, their directions of momentum is different. So you can also say as a difference that direction of momentum is different. I'm just writing abbreviations, don't write like this in the exam, but their momentum is different in terms of its magnitude and direction. The vertical acceleration of downwards is 2.5 meters per second squared. Calculate the tension in the string. So if we had to draw a free body diagram, we'll see that we have the load's weight that is pointing downwards, and then we also have a tension force that's coming from the pulley that is actually the box and the pulley that's pulling the load up. But what we'll see here is that the load is released, and when it's released, it accelerates downwards, meaning that the weight is ultimately larger than tension. So what we'll have to do here is mg minus t, so weight minus tension, equals m times a to calculate the actual tension. So our load was what, 3.5 kilograms times 9.81 minus tension equals, again, 3.5, and then our acceleration is 2.4 meters per second squared. So our tension comes about 26 newtons from here, and that is the tension in the string. Show that the speed of the load when it hits the floor is about 2.1 meters per second. Okay, so when we're trying to calculate the speed of the load here, we're just gonna think as if it was a free fall, because there is some tension from the string, but obviously the actual force that is acting on the load so that it accelerates downwards is the weight. So we'll just use the formula v squared equals u squared plus 2as. Okay, so the final velocity is one that we do not know, and the one that should equal to 2.1. It doesn't have an initial velocity, so u is 0, and then 2, the acceleration downwards is going to be 2.4 meters per second squared, and then the displacement, the distance that it falls through, is 0.95 meters, and this comes to something about, when we take its oh my god, I forgot the name. When we take its square root, it is going to be something close to 2.14. That is 2.1 meters per second squared. So the fourth question actually is the radius of the pulley is 2.5 centimeters. Calculate the angular speed of rotation of the pulley as the load hits the floor. Okay, so it wants us to calculate the angular speed. State your answer, la la la. Okay, so V equals angular speed times the radius, right? The linear speed equals. So that means the angular speed is going to be equaling to linear speed over the radius, and our linear speed was 2.14 meters per second actually when the load hit the floor, as the question says. And then our radius is 2.5 centimeters, which equivalates to 0.025 meters. And this is going to equal to 84 radians per second. So this is our angular speed. After the load has hit the floor, the box travels a further 0.35 meters along the ramp before coming to rest. Okay. Determine the average frictional force between the box and the surface of the ramp. Okay. So the question says the load has hit the floor. Let's say the box has come here when the load hit the floor. And then the question says it travels a further distance of 0.35 meters after the load has hit the floor. And here it has come to rest. Okay. So here the final velocity is going to be equal to 0 meters per second because the box has come to rest. Then here, because the load and the box are connected by a string and a pulley, 2.1 meters per second is going to be the initial speed of this moment because the speeds of both of the objects have to be equal when the load hit the floor as they are connected by a string and a pulley, as I've said. So from this part, you can both use v squared equals u squared plus 2as. This is a path that you can follow, but whenever a question like this occurs and you can't seem to solve it, I suggest that you always use energy, conservation of energy. So you can basically say here it had a kinetic energy of this, and here it has this, and blah, 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 because energy always has to be conserved. So what we'll use here is we'll subtract the component of weight, the force that the weight actually puts on the box from the net force so we can find the frictional force. Why? Because, so this is how the weight is acting on the box, right? So weight has two components. So this component is acting downwards, and it's V sine 30. This is a mathematical explanation. You can just fact check it yourself if you can understand it. V sine 30, I'm sorry, I was going to say theta. V sine 30 is the component of weight that's acting downwards because the box wants to move downwards from the ramp. And the box is moving at this direction, which means the frictional force is going to be moving in this direction. So when you look at this picture, you can say the box is moving this way, but the component of weight and frictional force are at this way. So this means the net force has to be from the pull of this string bigger than the combination of the component of weight that's acting downwards and then the frictional force. So where will we use all of this information? Okay, so the first thing that we have to write is the net force minus the weights component down the ramp is going to be equal to our frictional force, as we've seen in the visual above. Then the next thing we'll do is when the box has traveled here, from here, we can calculate the kinetic energy that's formed in between. And we know whenever it asks us about an object that has come to rest after a distance, we can always use work equals change in energy equals force times distance. Okay. So we'll find the net force that is acting on the object from there. So the change in energy, so our initial energy, we say it's zero because we are just considering the moment from the moment it travels here to here. So it has zero velocity here. The kinetic energy here is zero. It's bigger here. So the kinetic energy that is lost here is going to be our change in energy, which is 1/2 times m, so 1.5 kilograms times 2.1 squared. And this is going to be equal to force times distance, which is 0.35 meters. So the net force that we'll have here is 9.45 newtons. And then when we subtract the weight down the ramp from the 9.45 newtons that we have here, The answer that we get is going to be 7.4, and this is going to equal to 2.1 newtons, which is the frictional force between the box and the surface of the ramp. The student then makes the ramp horizontal and applies a constant horizontal force to the box. The force is just large enough, so this is a very important keyword. The force is just large enough to start the box moving. The force continues to be applied after the box begins to move. Okay. Explain with reference to the frictional force acting why the box accelerates once it has started to move. Okay. So we know that mu static, the coefficient of static friction, is bigger than the coefficient of dynamic friction. So what this means is when an object is at rest, it has more contact points with whatever its surface it is on. So it is very much harder to move that object than an object that is already in some kind of motion, and it is not as hard to move it and move it against frictional forces. So the first thing that we have to say here is mu static is bigger than mu dynamic. So therefore, because of this, force of dynamic friction will be less than the force of static friction. As I've said, this will cause an unbalanced forward force in motion. So let's write all of this down. Force of static coefficient, I'm sorry, force of dynamic coefficient of friction will be less than the force of the coefficient of static friction, which will cause an unbalanced forward force that will cause the object to accelerate. So this is why the object accelerates once it has started to move. Thank you so much for listening, and see you guys in the next video. Bye.